Hello everyone. Today we will be discussing a really interesting question from JEE Mains PYQs. A uniform rod of mass m and length L suspended by means of two identical inextensible light strings, as shown in figure. Tension in one string immediately after the other is cut is. So you have to find the tension. That's the question. Now, if you look at this figure carefully, right now, imagine the string is not cut. Okay, so what happens at this instant? You can see the rod is perfectly uh, hanging with the help of both the strings on either sides, and the force is acting on the rod. If you consider, you can see there is a tension acting in the upward direction along the string, and there's a tension acting along the string, and there is weight of the rod which is acting on the center of mass in the downward direction. Weight, which is mg. M is the mass of the rod. G is acceleration due to gravity. If you draw the free body diagram of this rod, you will see that there are two forces acting in the upward direction. Assuming the tension on both the strings are same, so we can say two times of the tension in the upward direction, and there is the weight acting in the downward direction, which is mg. So since the rod is not moving, so we can say the forces are perfectly balanced, or 2t is equal to mg, or t is equal to mg by 2. You can clearly see that the weight is perfectly balanced and the tension is equally uh, dividing these weight among itself, right? So this is what happens when the string is not cut and when the rod is not moving. But what happens when the string is cut, when one of the string is cut? That's what the question is here. Let's check. So immediately after when the string is cut, let's assume that string at B is cut. String at point B or end B is cut. So if that is the case, so this one is cut, and immediately after the string is cut, we have to find the tension. Immediately, it's a very significant term, right? So if you look at the forces here, what are the forces acting right now? So there is no tension on this part of the string because it's cut. The tension is acting on this part in the upward direction at this point of contact. And then there is this downward weight acting. So if you draw the free body diagram, you can see there are two forces acting on this. There is a tension in the downward direction, tension in the upward direction, and then there is the weight acting in the downward direction. And the road will be having a downward acceleration. That downward acceleration because of the string being cut, and there will be a motion later on. But eventually there is an acceleration. So we can see if you write the equation of motion for this vertical direction, you will see the equation can be written as mg minus t is equal to ma, where a can be taken as the acceleration of center of mass in the downward direction. So this is the first equation, equation number one. Now you can see there is also, you can also visualize a kind of rotation happening here because this part of the B can come down and this part of A can go up. So if you write the equation of torque here, we know torque is equal to I alpha, right? So this is the analog of second law of motion and rotation, as you know. And this torque we can calculate about any point on this road. So to make it easy, I'll calculate the torque about the center of mass of this road. So what are the forces acting about the center of mass? Currently, we know only two forces are acting. Mg is acting as well as the tension in the upward direction is acting. Since mg is acting on the axis of rotation we have considered, the torque due to mg will be zero. But there will be a torque due to tension. So that torque I can write it as torque is force into distance from the axis of rotation. So tension is the force multiplied by the distance from the center is half of the length of the road. So L by 2 is equal to I. I is the moment of inertia of the road about the point which we are considering the rotation. So moment of inertia of this road about this axis is the center of mass is ml square by 2 as you have studied, ml square by 12 into alpha. For simplifying this relation, we can write this as 2, 6, L cancelled out. So I can write an expression for alpha from this. I can write alpha as alpha is equal to 6t over ml. 6t over ml. Let's take it as equation number 2. Now, if you look at point A, point B is going down, but you can see that if you consider this point A or the end A of the road, it's still connected to the string, which means the net acceleration of point A will be 0, right? So if you consider the acceleration of point A, net acceleration of point A, that will be equal to 0. And we know that net acceleration in any case about for any point is given as acceleration of center of mass plus acceleration of the tangential acceleration, right? In rotation, you have studied this. So, for example, if you consider a disk rolling, okay, or a sphere rolling, if you consider the disk to be moving in this forward direction as well as rolling in this direction, so you will see that if you consider any point here, let's say you consider the point A, this point A here. So for this point A, you can see the net acceleration of point A. We have studied it in the chapter rotation, that the net acceleration is given by acceleration of center of mass, which is the overall acceleration of the disk in the forward direction, plus the acceleration of the tangential acceleration of that point with respect to the rotation. And the tangential acceleration you've studied, that is r alpha, where r is the distance from the point of rotation. So acceleration of net acceleration, as we have seen for point A is 0, since it's still connected with the string. So this is equal to acceleration of center of mass, plus or minus tangential acceleration, which is r alpha. Why minus? Because you can see both are in the opposite sense here. Because if you consider this point A, since B is about to come down, acceleration of point A is a bit upwards. It's supposed to go up, right? And the center of mass acceleration is in the downward sense. So since both are opposite, we can take one to be negative. And we can say acceleration of center of mass is equal to r alpha, or r is L by 2 here. So L by 2 alpha is the value. Sorry. So this is the acceleration of the center of mass. Now, from this, I can also substitute for alpha in here. So this becomes L by 2 into alpha is 6t by ml, or this L cancelled out to 3. So this is 3t by m. Okay. So you can see that if you put this acceleration equation, let's call this equation 3. If you put this equation 3 in equation 1 as you can see is this. So if you put that equation in equation 1, I just write equation 1 again. Mg minus t is equal to m into acceleration of center of mass. Substitute that here, m into acceleration of center of mass 3t by m from equation 3. Or I can write this as mg is equal to t plus 3t is equal to 4t, which means t is equal to mg by 4. This is our final answer. So hope it's clear. If you quickly summarize what we have discussed, you can see that initially we have taken the equation of motion in translational sense. The force acting mg and t in the opposite directions is equal to m into acceleration of center of mass. And we formed the equation using torque, the rotational analog equation, and found the equation for expression for alpha, and use that expression for alpha in the acceleration of center of mass, right? And again substituted that back into the equation of motion to get the final equation for tension. Hope it's clear. Thank you.